Okay. We have one more definition. A sequence may not be increasing, may not be decreasing, may not be positive, or may not be negative for all terms, but sometimes there is an index, and after that index, the sequence becomes positive or negative or increasing or decreasing. In that case, we say that the sequence is ultimately positive, ultimately negative, or ultimately increasing or decreasing. So let me write it this thing. Okay, the adverb verb ultimately is used to describe any uh, term-wise property of a sequence that the terms have from some point on, but not necessarily uh, at the beginning of the sequence. Examples, look at this sequence, n minus 3. Okay, what are the terms of this? When you plug n equals 1, you get minus 2, and then minus 1, 0, 1, 2, 3, and so on, right? This sequence is not positive. However, after the third term, right, all the terms are non-negative. The first two terms are not positive, but after the third term and on, they are positive. Therefore, this sequence is ultimately positive. Is not a positive sequence because positive means all the terms should be non-negative. But it is positive after the third term. Therefore, we say that the sequence is ultimately positive. Okay. Another example, look at this sequence. Okay. And let's say this is 5, 0, minus 3, 0, 2, and then let's say minus 1, and then 0, 1, 2, 3, 4, and goes like this, and so on. So at the first terms, it is neither increasing or decreasing, right? Here the value decreases and then decreases again, increasing, increasing, decreasing, and then again decreasing. But after this point on, it's an increasing sequence: 0, 1, 2, 3, 4, and so on. And suppose that it goes like this, okay? Increasing with increasing values. So this sequence, yeah, sure. Huh? Okay. This sequence is, although it is not increasing, it is ultimately increasing because it becomes increasing after some point on. Okay? So if it is the case, then we say that it is ultimately increasing. Usually for us, it is the behavior of the sequence is the behavior of the sequence after some point on is important. So the first terms, first few terms are not really important. The important part is the tail of the sequence, the infinite tail of the sequence. Okay, that's why uh, even though a sequence may not be increasing, if it is ultimately increasing, then we may regard it as if it is increasing, although it is not. Okay, you will see what we mean by that later when we especially study series. So the sequence above is uh, not increasing, but it is uh, increasing after some point on, right? And thus it is ultimately increasing. Okay, right? After this point on, actually it is even this point, right? From -1, it goes to 0, 1, 2, 3, 4, and so on. So after this point on, it is increasing. So it is ultimately increasing, although it is not increasing sequence. Okay. Sorusu olan any questions so far? All right. We have one important concept called the convergence of sequences. So let me write that down. Convergence of sequences. This is something similar to the convergence of a function as x goes to infinity. Okay, let me write down the definition. We say that a sequence uh, an converges to the limit L and write limit as n goes to infinity an equals L, provided that the distance from the nth term of the sequence an to L on the real line on the real line approaches to 0 as n increases toward infinity. Uh, this is not a mathematical definition. This is a description of what limit is. Limit of an is equal to L means the following. You look at the distance between an and L, and if this distance goes to 0 as n increases, okay, then we say that, okay, an has limit equal to L. The mathematical definition is the following. Okay. We say that uh, the sequence an converges to the limit L, and we write limit as n goes to infinity an equals L if for every positive real number epsilon, there exists some integer n uh, so which may depend on epsilon. So the choice of this integer may depend on epsilon, okay, such that if n larger than or equal to n, then the distance between an and L is less than epsilon. Okay, so that's the mathematical definition of limit. So what it means, suppose this is our limit value L. For a sequence to have limit equal to L as n goes to infinity, you should have the following. Whenever you are given an epsilon is any positive real number. It can be a big number or a small number, anything you want. Whenever something like this is given, you draw this neighborhood L plus epsilon, L minus epsilon, and you should have the following. The terms of your sequence should fall into this interval after some index on. In other words, your sequence should be ultimately inside this interval. Okay, there can be couple of terms left outside this interval, but all the terms after finitely many terms should fall into this, and this is stated as follows. So there is some n, so that an minus L is less than epsilon if n is n or bigger. So an should be somewhere here. An minus 1 maybe is somewhere here. An plus 1 million will be here. all the terms of the sequence after the nth term should fall into this interval. And this should hold for all epsilon. You may give me another epsilon, then I'll choose another n. Okay, so this is like a game. You give me epsilon, I choose n. So that all the terms of the sequence after that term on falls into this epsilon neighborhood of the limit value. Okay, if I can find an n value for every epsilon you give me, then I will win, and I'll say that the limit of an is equal to L. And if I cannot find some n for a specific epsilon you give me, then you win, and in that case an is not doesn't converge to L. Okay. Uh, okay. Some examples. For example, look at this sequence. 1 over n. So this is 1, 1 over 2, 1 over 3, 1 over 4, and so on. Okay. Uh, can you guess the limit value for this? What is the limit? Limit of 1 over n as n goes to infinity should be 0, right? You divide 1 into n pieces, and n is getting larger and larger, and the limit will be 0. Actually, if it were not 0, then it would be great, right? Then we could share one piece of anything with many people, and everyone would get something, something which is not very small. But that's not the truth, of course. If you divide a fixed length into smaller and smaller pieces, eventually all those pieces will goes to the length of these pieces will go to 0. Uh, can we prove this fact using the mathematical definition? Let's try that proof. So what we should do, you should give me an epsilon. I should find some big N, so that after that N, all the values of the term should fall inside that epsilon neighborhood. So given epsilon positive, okay, uh, yes, this one, a n plus 1 million, 10 to the power 6. Okay, so a n will be inside this interval, n plus 1, n plus 2, n plus 3, n plus 4, all of them. Okay, so if you give me this epsilon, what I want is this. I want a n minus L less than epsilon. Well, a n is 1 over n, and L is 0, and this should be less than epsilon. So this means 1 over n should be less than epsilon. Therefore, n should be, right, larger than 1 over epsilon. So this n should be larger than 1 over epsilon. Epsilon could be something very small. It could be something, for example, like this. So in this case, n should be what? 1, 2, 3, 4, 5, 6. Right? It should be 1 million. So what I will do, I will choose my n, big N, an integer larger than 1 over epsilon. So this is what I will do. Uh, you gave me this epsilon. I did my computation over here and understood what should I write down? And then I do the following. Choose a positive integer so that n is bigger than 1 over epsilon. Whatever your epsilon is, I'll choose something bigger than 1 over epsilon. Okay? Then, if n is larger than n, right? This is my definition. When you give me an epsilon, I should choose some n so that if n is larger than n, then an minus l should be less than epsilon. Let's see if I can do that. So if n is larger than n 0, then let's see an minus l. What is this? This is 1 over n. L is my limit value, which is 0. So L is 0. Okay, so this is 1 over n. But you see, n is smaller than little n. Therefore, this is less than 1 over n, right? Because n is larger than, small n is larger than big N. Therefore, 1 over n is less than 1 over big N. But this was chosen so that n was larger than 1 over epsilon. If n is larger than 1 over epsilon, then 1 over n is less than epsilon, since n was larger than 1 over epsilon. Okay, so what we have seen is then, okay, you see my definition of limit is embedded into this argument. Given epsilon positive, I choose my n satisfying this condition. Okay, I can choose an integer larger than 1 over epsilon. Now, if this is larger than n0 n, then this is less than epsilon. So that's my definition of limit, mathematical definition. Therefore, we have proved that the limit of 1 over n is 0. Yani şunu yapmam gerekiyor. Verilen her epsilon için bir tane n bulacağım. Öyle ki küçük n büyük n'den büyükse bu fark epsilondan küçük olacak, right? So this argument gives me an n value for any epsilon you give me. Okay, no matter which epsilon you give me, I can find this n, and this is how I will find it. Look at 1 over epsilon and choose your n, something larger than that. I can do this because the natural numbers is unbounded. Therefore, whatever that number is, there is always a natural number larger than that number. And I'll choose one of them. And then if n is at least that number, then this difference is less than epsilon. Okay? This is the mathematical definition. And in math department, in the courses we teach, calculus or mathematical analysis, this is what we expect from students actually. This we want them to give proofs like this. But in this course, we don't require that. But still, you should keep in mind that this definitions of limits and these concepts are well-defined objects in mathematics, okay? Even though we don't require these in calculus courses, mostly they are, well-defined objects. Okay. Uh, More examples. not epsilon delta examples, but n minus 1 over n. What is this sequence? So this is 0, 1 over 2, right? 2 over 3, 3 over 4, 4 over 5, and so on. What is the limit of this? Can you tell me what is the limit of this? 1, right? We can actually see it also this way. You see n minus 1 over n is just 1 minus 1 over n, and we have seen that 1 over n, this goes to 0, right? 1 over n. Therefore, since 1 over n goes to 0, this goes to 1, okay? Another one, n, so 1, 2, 3, 4, and so on. Is this sequence converges somewhere? Right. This doesn't converge to any real number because the values are nothing. They are not getting closer to a real number, right? They are just going to infinity. So this is a divergent sequence. This diverges to, we say, infinite. It goes to infinity. If a sequence is not convergent, then we say that it is divergent. Okay. I guess I didn't tell you that. Okay. I will. What about this sequence? This is minus 1, minus 2, minus 3, minus 4. This is also divergent, but this time it diverges to minus infinity. What about this one? So this is minus 1, 1, minus 1, 1. So it's an alternating sequence. It's plus 1, minus 1, plus 1, minus 1. And this sequence doesn't get closer to any real number either, right? So it just keep uh, going from 1 to minus 1 and so on. So this is not divergent. This is not convergent either. Uh, uh, is divergent. For it to be convergent, the terms of the sequence should be arbitrarily close to a real number. But here, the terms of this sequence are not even close to each other, right? They just go like this. They doesn't get closer and closer to any real number. Therefore, it is divergent. Uh, no, look at this one. So this is minus 1, 1 over 2, minus 1 over 3, 1 over 4, minus 1 over 5, and so on. Right? The terms are going, this is an alternating sequence also, but all the terms are getting closer and closer to 0. So this is a convergent sequence, right? Is convergent. Convergent with, what is the limit? Minus 1 to the power n. This is just 0, right? The limit is 0. Okay. So here I should maybe write as a remark. If a sequence is not convergent, then we say that it is divergent. Okay? Or we say that the sequence diverges. Sometimes it diverges to plus infinity, sometimes it diverges to minus infinity, or sometimes it doesn't diverge to neither plus or minus infinity, like this one, right? It just goes from 1 to -1 and then -1 to 1. It goes like this. So it is just divergent. Okay. We have a fact. If an, if a sequence an is given by a function f from R to R, that is an is just f of n. So there is a function so that its value at n is equal to an. And if this function has limit at infinity, if limit as x goes to infinity of f of x is equal to L, then an is convergent and limit an is equal to L, right? Here is what happens. Suppose this is our L. And we have a function so that this function, is something like this. Okay. So, and here, so this is, sorry, this is y equals f of x. This is the x-axis. This is the y-axis. And my sequence is like this. So this is, let's say, 1, 2, 3, 4, 5, and so on. And so A1 is somewhere here. This is my A1. Okay. So okay. The values of my sequence are like this. A2, A3, A4, A5, A and so on. And you see, as n goes to infinity, of course, n goes to infinity. And in that case, the values of f gets closer and closer to L. Therefore, an values will get closer and closer to L. Therefore, an will have limit equals L, right? This an is somewhere here. It will converge to limit value of f, which is L. Yani eğer elinizde ki dizi bir fonksiyonla veriliyorsa ve fonksiyonun sonsuzda limiti varsa o zaman dizinizin de limiti var. Çünkü işte x yerine n'leri de yazabilirsiniz. Değil mi? X sonsuza gidiyorsa x sonsuza giderken aldığı tam sayı değerlerini yazarsınız. O da dizinin değerlerinin L'ye gittiğini söyler. Okay. Rules for limits. Suppose that an and bn are convergent sequences. Okay. Then we have the followings. Then first an plus minus bn is convergent, and limit of an plus minus bn is equal to limit of an plus limit of bn. So if you have two convergent sequence, by adding the terms of this sequence, you obtain another sequence. And if an and bn are convergent, then so is their sum. And the limit of the sum is just sum of the limits. You can also look at the difference, and in that case, the limit of the difference is the difference of the limits, right? Limit of the difference is the difference of the limits. Similarly, you can multiply two sequences. This is also convergent, and the limit of an times bn is just limit of an times limit of bn. So in other words, the limit of the product is the product of the limits. Okay. Limit of c times c times an is just c times limit of an, where c is any real number. Any real number. In other words, you can multiply the terms of your sequence by any number you want, by 5 or minus 10 or 15, whatever. You obtain another sequence, and that sequence has also limit, and the limit of the new sequence is just c times the limit of the original sequence. Okay. In other words, if a sequence is convergent, then you can multiply it by any number you want, and the limit is just that number times the limit of the sequence. For the ratios, you have to be careful because you divide two real numbers, and you don't want to divide by 0. So if an's are never 0 for all n or all n, and if limit an is not 0, then the sequence an over bn is convergent, and limit of an over bn, this is just limit of an divided by limit of bn. I should change this to bn. Okay. Because I divide by bn. Okay. You don't want to divide by 0 if the terms of the sequence bn are never 0, and if the limit is not 0, right? The terms of the bn are not 0 doesn't imply that the limit is not 0, right? Consider the sequence 1 over n. They are all positive numbers, but the limit value is 0. So you don't want that sequence. In that case, the ratio of an, bn is a convergent sequence, and the limit is just the ratios of the limits. Okay, we have also this. If an is less than bn, ultimately, then limit of an is less than limit of bn. And similarly, if an, bn, cn, ultimately, then okay, and limit of an is equal to limit of cn, which are both equal to l, then uh, bn is convergent. Şunu şöyle yazayım ya, bu biraz kötü oldu. Cn bn diyeyim. So then Cn is convergent and limit of Cn is equal to L. So if you have two convergent sequences, An and Bn, and if you have a third sequence whose terms are always between An and Bn, but actually that's not the assumption. We ask ultimately. It means that for the first 100 terms or 2 million terms, this may not hold, but suppose that this holds ultimately. So there is some index, and after that index, we have this inequality. In that case, if an and bn has the same limit L, then the sequence squeezed by these two sequences is also convergent, and it has the same limit. Why this is true? Well, it is true because we say this is true ultimately, this inequality. Ultimately means if n is big enough, then I have this. And when we take limit, we let n go to infinity. So n will get bigger than any number you want. Therefore, if this holds ultimately, it will hold for the terms that will count for the limit. Therefore, the limit of this will be less than the limit of this one, but they are the same. Therefore, the third sequence in between should converge to the same number. Evet. Yeah, it is the squeeze theorem. Yes. Yeah. Uh, so here is what happens. So here, let's say I have an, bn, and there are cn's here. Okay. an goes to L, bn goes to L. Therefore, this cn will have no choice but approach to L. Uh, this is called the sequencing theorem. Bunu yanlış yazıyorum herhalde ama squeezing 2e olacak değil mi burada? This sequence Cn is sequenced by An and Bn, and both of them goes to the same place. Therefore, anything between them will go there. Okay. Okay. I have only 2 minutes. Let's give a break. After the break, we will continue. Okay, let's break.